By far, we have talked about frequency distribution and measures of central tendency. And next, we're going to talk about measures of dispersion. This is also one of the description for this set of data. So we're going to cover two measures of dispersion, range and standard deviation. Range may be the simplest and easiest to calculate of the measures of dispersion. So range is defined as the difference between the largest and smallest value of your dataset. So the XH stands for the highest observation in a series, and XL is the lowest observation. So you use the difference between them to define the range. Another measure of dispersion is standard deviation. Standard deviation is a numerical value in the units of the observed values that measures the spreading tendency of the data. So why we use standard deviation here instead of just deviation? We use standard because the result, this value, is in the same units of your data points. And if we have large standard deviation, then we're going to have greater variabilities of data. So the data is more spread out from the average of the sample. And this is the definition for the sample standard deviation. It is the square root of this ratio. So this ratio is defined as the sum of the sample data minus the average of the sample to the square, divided by n minus 1. So why we're using n minus 1 instead of n here is because the x bar is also a function of xi's. So x bar is defined as the sum of xi's divided by n. Therefore, we lose 1 degree of freedom. So we're not dividing n, but n minus 1 here. I'm going to use this example to demonstrate the use of standard deviation. So assume that we have manufactured 6 parts, and they have their weight recorded in kilogram. So the average of the weight is 3.0. So you sum up all these 6 values together and divide it by 6. That gives us 3. So now I want to measure the dispersion, or the distance from the data points to the average. And therefore we use our data point xi minus the x bar minus the average. So that gives us this series of numbers, right? So for example, 3.2 is 0.2 away from our average. And this 2.9 is 0.0 less than the average. So why we're using the square here is because it can give us a positive number for each distance. If you just use the differences between xi and x bar, then if you sum up them together, the plus and minus will cancel each out. So you cannot find any difference to the mean. And therefore we put a square for each of the difference, and then it turns everything to a positive number. So if this positive number is large, then that means this data point is more far away from the average. If this data point is small, it can be no less than 0. So if it is small, then that means this data is close to the average. And so now if you sum up all this xi minus x bar to the square, and then you can get this sum here in the numerator, which records the total distance from the data points to the mean, and where the distance is measured in this form, xi minus x bar to the square. So if you notice that this value that we calculated is in the unit of kilogram square, right? So it is no longer the same unit as our observed data. And that's why we need to put a square root here to make the standard deviation having the same unit as our observed data. So if you put a square root here, this standard deviation S is also in the unit of kilogram. So here is our calculation. The numerator, this sum of xi minus x bar to the square, is recorded here in our table, the sum of this column, right? And then divided by n minus 1, which is 6 minus 1 equals to 5. So we use 0.080 divided by 5, and then we get 0.016 kilogram square. And then the standard deviation is the square root of the first part. So we take a square root of this, and then it gives us 0.13 kilogram as the standard deviation. For ungrouped data, we can use this formula in place of the definition. They are actually equivalent, but in this formula, we eliminate the x bar. So you can just use the data points x1, x2 up to xn to compute the standard deviation. So you do not need to compute the x bar first and then compute the standard deviation. You can just use these xi's. So this slide shows the equivalency of the sample standard deviation and the formula for the ungrouped data. So they are essentially the same. I do not require you to make this proof. This is just for your information if you are curious why we can use both of these formulas. So the most important technique that we use here is to process the numerator in the square root, this part. So we replace the x bar by the sum of xi's divided by n. See? We replace the x bars by xi's, and therefore we can find some equivalent form just written in xi's, just written in the data points. And here's an example for the ungrouped data. So determine the standard deviation of the moisture content of a roll of craft paper. The results of 6 readings across the paper web are 6.7, 6.0, 6.4, 6.4, 5.9, and 5.8. And they are all in terms of percentage. So the unit of our readings are percentage, and they are actually standing for 6.7 percentage, etc. So now, using the formula for the ungrouped data, you do not need to find the x bar, the average, first. So you can just use, you just need to plug in these xi's, right? So for the first term, you use the xi square, that is the 6.7 square, plus 6 point square, plus 6.4 square, plus 6.4 square, plus 5.9 square, plus 5.8 square. This will give you this sum, right, which equals to 231.26. And then times n, which is 6 here, n data points. And then minus this term, and this term is computed as the sum of xi to the square. So you must differentiate these two terms. This square is placed for each individual xi. This square is placed for the sum. So you need to first compute the sum of these 6 values, which equals to 37.2, and then you place the square to this sum. Okay. And for the denominator, we use n times n minus 1, which is 6 times 6 minus 1, right? And then you take the square root. So the final result is 0.35, which is also in the unit of percentage. So the standard deviation is 0.35 percentage for our set of data. For grouped data, we have a formula that is similar to the ungrouped data. So here, instead of using the individual xi's, we use Fi times Xi, and the Fi and this H stands for the number of cells or classes that we have. The Fi is the frequency of class I, and the Xi is the midpoint of the class I. So here's an example. On the first column is the boundaries for each cell. We're recording the passenger car speeds during a 15-minute interval at this Interstate 57 at location 236. So all these speeds are classified into 5 classes, right? And each class has its lower bound and upper bound. And this Xi is the midpoint of each class. And this Fi records the frequency of each class, the frequency of the speed that will fall into the boundary of the class. Okay, the frequency of the speeds that is within this boundary. So what we need to compute is the sum of Fi Xi squared and the sum of Fi times Xi, and then put a square of the sum. Okay. So for our computations, you need to record these 2 columns. So this column computes the Fi times Xi, right? So you just use this column, the value in this column times the value in this column. And this one computes the Fi times Xi squared. So for example, the first one is computed by 5 times the square of 77. Okay, so it's the same as 5 times 77 times 77. And that gives us 29,645 here. So you go on this way and then you find all the Fi times Xi squared. And in the last row, you compute the total. So the total of the frequency, you sum up all the frequencies, that will give you the total number of data points, right, which is 96. And you sum up the Fi times Xi, which is 9,354. And then you compute the sum of Fi times Xi squared, which is 920,742. So now you can plug in all these numbers. This is the n times this sum, right? This is the n times this sum. So you use 96 times this value, and then you minus the square of the sum of Fi times Xi. So you use this value here, put in the parentheses, and compute the square of this value. Okay, and divide it by n times n minus 1, so which equals to 96 times 95. And we put the square root here. That gives us 9.9 kilometers per hour. And this is the standard deviation that we have. For your information, I also recorded the average here. So after we have talked about the range and standard deviation, let's discuss the relationship between the measures of dispersion. So the range is a dirty and quick method to measure the dispersion. As n increases, the accuracy of range will decreases. So when you have more and more number of data points, it becomes easier for extremely high or low readings to occur, and that will result into an enlarged range to incorporate those outliers. Therefore, we only use the range when there is a small amount of data or data is too scattered. So if the n is greater than 10, then we do not want to use the range. Instead, we use standard deviation. So a smaller standard deviation means better quality, means all the data points are closer to the average, they are not too spread out from the average. Here are two graphs that is having the same range. You see, the numbers, the possible numbers that it covers are the same. And they also have the same mean, the x bar. However, they have different standard deviation. As you can see, this one has a lot of outliers in the tails, right? So it has a larger standard deviation than the second graph. The second graph has more data that is close to the x bar, to the average. Okay, so for example, something like this may look like a data set of 12, 12, 14, 16, 16. So the average is 14, right? And the range is 4, 16 minus 12. So we compute the standard deviation, which is computed using the definition, right? We use each data point minus 14 to the square and sum them up together, and then divide it by n minus 1. So we have 5 data points, minus 1 is 4, and then take the square root to find the standard deviation, which is 2.0. And now, as an example of this kind of data set, we have 12, 14, 14, 14, and 16. So the mean, the average is still 14, right? And the range is still 4, 16 minus 12. But the standard deviation is smaller, it's only 1.4. As you can see, because all these three numbers are the same, identical to the average, so we have a lot of zeros here. Therefore, this standard deviation is smaller than the first data set. So in this case, using range cannot differentiate the dispersion of these two data sets, but if you use the standard deviation, you can tell that this set of data has better quality than this set of data.